found when everything is in equilibrium, you actually could not tell time because there's no change to some extent, or no kind of change which you could reference the passage of time to. Yes.
Paul, thank you so much for that insight, perspective, and that guidance. Your presence, leadership, and energy is so amazing. Thank you. Alexander, back to you, sir.
Oh yeah, thanks, Jonathan. Yes, Paul. Yeah. So Paul, I guess I have a question regarding I guess the definition problem of time. So you've referenced some baseline clockwork, um, and then you just defined the current time models as essentially being discretized. So I guess the question I have for you is, if I was to ask you to formalize time at the most fundamental level, um, what do you think that would be if we were to go beyond the concept of energy, for example, as an abstraction or an analogy? Um, um, what are your thoughts on that?
Okay, so I think there you kind of packed a lot of things into this question. I remember kind of also our discussion from kind of the last time, where your kind of your questions were like were pointed at kind of this difference, or you called it duality or polarity of kind of perceptions or models of kind of time. And yes, like maybe should first say like how kind of time enters physics, and it does so by basically being considered like a continuous real parameter. So like some number, like a real number, which can be kind of infinitesimally small, resolved, that basically runs from minus infinity to plus infinity in most physical models. You could say, okay, it starts with the beginning. There's like kind of a t equals 0, which is the Big Bang, if you kind of go to cosmology, but mostly in physics, you would just consider it as like kind of this kind of continuous parameter. That for if you kind of include relativity theory, kind of can kind of change its behavior or kind of relative behavior to each other if you kind of consider every space-time point or every object in space-time to have its own proper time. But it does not change much about kind of uh, the fact that it's still a continuous parameter. And so quantum mechanics actually arose or can be mathematically seen as a kind of a quantization of this kind of let's say continuous parameter that exists in classical physics, for example, as momentum or space or energy. And the funny thing is that actually, like the only parameter that survives kind of this process when you kind of derive quantum theory, kind of unharmed is time. So time also in quantum mechanics is still kind of a continuous parameter. And this makes it kind of quite mysterious to some extent. And this also goes like, so quantum theory is kind of the most effective and kind of accurate theory we have derived so far. So like like we have not kind of found any experimental contradictions or kind of fact that we could not explain in the regime that we think that it's valid so far. Everything seems to be work out fine. Still, I think it's kind of this polarity thing, or like kind of maybe kind of a little tension between kind of what theory and kind of experiment says. Like for me, this is like this kind of continuous parameter is kind of a convenient fiction, as like all experiments we can do in the world are like always only give us discrete values. Like there's kind of, as far as I know, no way where how we can really kind of
Paul, sorry for interrupting you.
yes.
Sorry, thanks for saying that, and precisely, and I think that's where that's why it's hard for me to reconcile a lot of the sciences with the formalization of time, because I think it's impossible to to be able to represent the completeness, and like you said earlier, and the consistency of this fundamental time in any discrete format. So the question then, so shouldn't the question then be, what is the most fundamental representation in a discretized format? Wouldn't that be the question?
That's a good question, but as far like there's also kind of attempts to do this, but it's a very difficult problem because, as I said before, like quantum theory as is kind of works pretty fine. So like if you kind of do the same thing with a discretized time, it can only make your life harder. But still, kind of, sorry,
Yeah,
just to come back to this point, it's like about kind of measurement or observing the world, is that for me, like all measurements we do, all observations of the world we can do, basically always give us discrete outputs. So we are not able to kind of resolve like continuous variables, or like kind of we cannot perceive kind of something that really amounts to a kind of a real number, in the sense that we have infinitely many digits after it, because there's always kind of a bound on the resolution, or yes, and also measurement error to things. I don't know if this answers the question.
Oh no, that was
Okay.
Jonathan, you want to jump in? That answered the question perfectly, Paul. Thank you. I'm going to jump in after Jonathan asks his question.
Oh man, thank you, Paul, for being here. This just is mind-blowing to say the least. That's an understatement, by the way. Well, let me ask you a quick question, right? So, in the world or the universe that we live in, there is maybe two actors, an observer and an agent. Would you agree with that statement? Maybe there's more, but I think there's an observer and an agent. Would you agree?
I'd like that's a hard question, because kind of it goes exactly to the kind of the borders, or kind of the edge of what we're able to say with quantum mechanics or within quantum mechanics. Like for me, these two kind of notions would be actually the same. Like somebody that observes, or like an entity that observes something, is actually an agent. Like maybe the people use this differently, because an agent is kind of associated with kind of something like a choice, and an observer is kind of passive. But I think I would interchangeably use these two notions.
Got it. Thank you for that. Thank you for that confirmation. So maybe last question for me at this moment, which is that when you say continuous, do you think infinity is continuous? I'm trying to discretize this and try to come to a definition. Would you say continuous is infinity?
Um, no, but you need infinity to kind of have something continuous, and you actually need more than infinity, because I don't know how far your knowledge goes about this, but there's kind of different kinds of infinities. No, like there's, for example, the infinity of the natural numbers,
Yep.
which is basically like which are countable, so I can kind of count until I reach infinity and can continue counting.
Yep.
And then there's infinity that are kind of that are not countable. Like for example, the amount of net counting could kind of have a discrete system.
So
So,
so so
but it also may turn out that kind of maybe like even thermodynamics kind of are kind of like a really weird theory, in the sense that the first, like it holds since its inception, and there's kind of two kind of kind of course kind of perspectives you can take on this. Like one is basically that it was formulated in such fuzzy terms that it applies nearly everywhere. And the second one is like maybe there's kind of something that kind of underlies thermodynamic laws, which has to do, for example, with just kind of a logical facts or computational facts that lead to this behavior.
Nicely said. So okay, so you mentioned computation and
Yes.
logical. So the reason why I actually brought up brought up this fundamental formalization is because you talked about measurement time. You mentioned measurements quite a few times, and when
Mm-hmm.
I hear the word measurement in my head, I'm thinking if you're going to measure something, then this thing already existed or precedes its measurement. Would that be an accurate assumption? That's why I
Uh,
have a time.
like the property, yes, but maybe it's the value not. As with like in quantum mechanics, you can take the perspective that kind of the value of the measurement actually comes like kind of emerges with the act of measuring. Um, but the properties, yes, like I think, but in the same way that that for
So
example
so
pressure does, no, like
so you're
maybe
saying
you
that
don't know the.
value is still going to remain married. It's still going to remain married to to this fundamental formalization, despite the fact that it's being measured. The measurement is just a discretized representation of that. Is that what you're saying? So the system still remains married or entangled together.
Yes, probably yes, or it's still subject to uh, kind of the mechanisms or laws that that govern this behavior. I don't know if this makes
I'm
sense.
sorry, I missed that, Paul. I was getting a call, so
Ah,
my phone got
mhm.
muted.
So like I think it's kind of it will be still be subject to kind of these laws that govern this behavior. So if you think of time as kind of a law or a mechanism that governs the behavior of systems, in this sense, I think it will kind of continue to hold true, even if we discover more underlying kind of mechanisms or laws or behavior of things.
Thanks,
So
Paul.
it seems, yes, it seems like the same way for like the second law of thermodynamics. No,
Mhm.
even if we find out, like it could also be reversed. I don't say that it's not possible to break the second law, but I think it's for all I can say, it's basically possible. And even we
Wait,
find
so Paul,
kind of
Paul,
a
it's
way to
Paul. The
describe,
thing is, in
yes,
thermal, it's not about possibility; it's about efficiency, right? It's just not efficient to go backwards in time. Would that be correct?
um,
It's possible. It's just
yes,
not efficient,
hmm,
right?
uh, efficient. Yes, maybe you could put it in such a way. Yes, I would not
So,
object. Uh,
so from an efficiency
like the only thing
perspective,
that
right?
tells me, the only thing that.
So sorry,
Mhm.
Paul. From efficiency perspective, can we then model that with complexity? If we're gonna if we can accept that efficiency is a good framework, right? Then can we then use complexity to model the same concept, and then use efficiency of the of to understand the dynamics of that?
So efficiency is like uh, a very thermodynamic concept, no? Like you basically measure the ratio between in and output of energy or whatever you resource you use. Um, so and or you could take it in a computational sense, but then it would just measure kind of the number of steps, kind of how this problem scales. And if it scales okay, you would say it's efficiently computable. Um, so
No, that's the
where I
right
was,
direction. I
yes,
like that. I
yes.
like the computational complexity direction. I think
Mhm.
that's a good. So from that direction, then can we then model the same concept out with algorithms, and then sort of figure out the optimal, or the baseline efficiency, the baseline algorithm that we could derive all the subsequent algorithms from, that would be discretized and thus less efficient as opposed to the baseline.
Yes, but the problem is that, like in algorithmic kind of computation, you have a measure of complexity, actually, no, like the Kolmogorov complexity, which is which gives you the program, the shortest program that can basically like output a certain bit string. That's the Kolmogorov complexity of an infinite bit string. The problem is just it's provably uncomputable. So, like, uh, it's a very nice measure. You can kind of do very nice stuff with it, but but you can effectively never really use it, no?
Exactly. It's the incomputability problem, right? It also goes down to in computation the fact that the machines are finite state machines. So I know
But it's
but
not it's not only a finite state. Like you have like the Turing machine. Yes, like it comes down maybe not finite state, but like to also to the problem that basically Turing machine is uh, kind of is subject to the halting problem, which basically like is a reformulation of the incompleteness theorem. Yes.
correct. So now that boundary that we're referring to, this boundary that we just hit with computation, the same boundary that we hit in the thermodynamics framework that you talked about earlier. Would you say that this boundary is the same boundary, sort of philosophically?
Mm, I
So,
think
so
we're
let, let,
not
let, me let, let,
there
let
yet,
me
like
elaborate. Let me elaborate,
because
Paul. Let me
yes,
elaborate. So,
mhm,
for
yes,
example, we have so algorithmic efficiency. As you mentioned earlier, computationally, we can model the efficiency by optimizing the time and space complexity of the algorithm, right? And I was saying that because we talked earlier about sort of if we were gonna go backwards in time in the universe, that it wasn't impossible; it was just not efficient.
yes, like in a hmm, it depends on what kind of assumptions you make about the world. No, like if you think we live in a deterministic world, then actually this kind of backward forward doesn't make any sense at all. It only makes sense if you assume that you like kind of the world kind of has there was at least one random bit in the universe, and uh, kind of that kind of there are irreversible processes. And you're right, like irreversibility just kind of to some extent in most formulations is more a probabilistic statement than kind of a fundamental one. uh, in this sense, you're right. I'm just very like I find it hard to kind of combine these notions in this context. Uh, yes, because I don't see that they kind of apply to the same objects, kind of in the sense in mathematical objects or objects that that yes that exist in some theory.
No, that's a valid point. That's a valid point. And I said that because I was looking at Turin and Goodell. They talked about the boundary that I'm referring to, and they approached this boundary from different perspectives. And Turing, like you mentioned, with the incomputability and the Houghton problem, is that there's a wall there. There's a wall. There's a wall in computation. There's a wall in physics. There's a wall that we keep knocking, and it's difficult to unlock what's on the other side of this door. And that's that's where it's very hard for me to reconcile that there's not something beyond that, right? And if there's something beyond that, is it a matter of access, or is it like what exactly is the issue that academia has to solve here?
So yes, so but like of course you could just kind of speculate about kind of the existence of super Turing machines that basically can compute these things. That, but I don't like think that like we don't see any kind of indication that such things exist in nature, or like that we kind of observe. But on the other hand, I don't know. I would not describe it as a wall. I would rather like both problems kind of they don't give you a wall. They just say like within kind of a system of a certain size, like a kind of a Turing machine of kind of a certain size, or like a mathematical theory with a certain amount of axioms, you cannot express kind of all the things you want to do, or you cannot kind of compute the probability of a certain program to stop. But what you can always do is add one more, and that's this kind of wall thing that you describe. Is for me is actually kind of something that we try like it's not so much a wall, but like if you kind of follow down this path of just kind of including one more axiom or kind of adding like making your Turing machine a little bit bigger, you kind of end up in an infinite regression, and that's something normally people want to avoid when they do science, because it yes, basically never stops. Yes, so it's and
Yeah,
yes.
so yeah, and that's I think that's where my problem lies. Is it's the reduction. The reduction requires, like you said, adding one more variable, adding one more variable, adding one more variable, and in a way, I feel as though that actually makes the system less efficient. So I don't know. What are your thoughts on that?
If you kind of expand it, the, I'm, I'm sorry, like it's just hard for me
Oh,
to
let
kind
me
of
let, let, let,
think
let me
of
elaborate. Let me
yes,
elaborate.
efficiency in this
Yeah.
country. Yes.
So for example, let's use data for example. The more
Hmm.
data you have, the more efficient your predictions will be. If you and if you make a prediction beyond the bounds of your data, then the predictions are gonna be likely more likely to be useless because you've gone beyond the bounds of the training data. So what I'm saying
Yes,
is
but I
that
would use in this sense it would be accuracy, no? Like because like if you have enough data, then you can be accurate, and everything else that you probably would become inaccurate.
uh, uh,
Like
I don't understand.
the efficiency in this
Yeah,
sense would be
can you repeat that,
no,
Paul? Sorry,
because like
can you repeat that? I didn't understand.
so so in this sense, what you like were describing to me, I would not call efficiency, because efficiency would be for me, for example, how fast can you go through the data? That would be efficiency. If you have a lot of data and you make a prediction about something that you can predict with the data, it would be an accurate or kind of yes, like accuracy would be such a notion I would use in this sense, or precision. And if you try to predict something that is not included, then it would become inaccurate. But if you have the same amount of data and you can kind of chew through it or process it at the same kind of rate, it would like it's equally efficient. It's just that the result in one case is more likely to be correct rather than the process being inefficient.
It's interesting. And this goes to the problem in deep learning and AI research. Um, and I was
Hmm.
listening to I'm not sure if you're familiar with Francois Cholet, or a couple other researchers that have started to come to the realization that our current deep learning models are actually not continuous, that they interpolate and are incapable of actual extrapolation. And what this researcher Francois Cholet said was that this actually creates the same boundary that I was referring to with Turing and Gödel and the likes of that, the boundary that prevents the ability for the AI models to be able to generalize. And generalization in this regard, as far as Francois Cholet, is the ability to essentially solve or abstract problems or task specific problems without the need of constant stability of the variables, as you said earlier, always adding a variable, reducing a variable, and all this. So and the thing is, I'm actually in line with that, with that perspective, because um I think to be able to extrapolate beyond trained data, I think that's a key part to understanding the interactions of systems fundamentally. What are your thoughts on that, Paul?
Uh, yes. So I don't know this guy, but um, I think this goes a little bit like of like it just would say that I can just opinionate on it rather than kind of give like more like an educated guess rather than um, but yeah, I think like for me, like yes, like all these machine learning algorithms and stuff, they're very powerful and they can do a lot of good things, but uh, they're also like they inherit the biases that we kind of have in the data, no? Like uh, um, I don't know if it's such a philosophical question, or if I never really thought so much about it in a philosophical way, rather in a kind of technical or limitations way. Yes. So probably you all know the story about the kind of the biggest, kind of the first machine learning algorithms that basically as a data set used the Enron scandal emails. So most kind of text recognition programs and stuff like this are initially trained on like the conversation of white, rich, male, corrupt beings. But on a philosophical level,
Paul, you know what's
actually, I'm
interesting,
not.
Paul?
Yes,
Sorry for
yes,
interrupting you, Paul,
tell
but
me.
what's interesting
Yes.
is that I don't think we even have to get to the point of the individuals that are dealing with the data. I think the data itself is inherently incomplete. If we can agree on if we can invoke Gödel, invoke Turing, invoke Markov, I mean we can say that data is inherently not a complete representation of what we're attempting to model, right?
Most definitely, yes.
So doesn't that then sort of still allude to the exact same wall that you're alluding to when you talked about the time and the inability to essentially get a hold of that reference point, that axiomatic time to essentially be the north star for all the other discretized representations of time.
Maybe. I, I cannot definitely answer this question, but yes, like I think there's true. Like we always have to like deal with incomplete data, and kind of as scientists we kind of try to make the most out of it, and uh, that's why probably also AI will have its problem replacing us, because like sometimes you kind of have to look over like your own horizon to actually make sense of stuff. Um, and yes, I don't know, like philosophically, I, I don't know how to formulate this, but maybe you should go to kind of something. I don't know if you know the holographic principle, which would basically kind of to some extent contradict this. It's not something proven; it's something people assume. Uh, I think mostly in string theory, uh, but it's kind of that basically all information about a system is contained in its surface. I think it's more like a neat mathematical trick people use, and it did not lead to string theory to anything so far. So uh, yes, I'm happy to deal with the incomplete and the partial data I have about the work to try to make the most out of it.
Yeah, yeah. Understood. Yeah, I was just asking because if it's time to create a self-contained model for clock, like you said,
Mhm.
I think that's a crucial part, right? You cannot do that with discretized models.
No, but so basically our model is discretized. It's the only way, like kind of we kind of escape completely, kind of like, or staying operational in the sense that we can kind of also measure the behavior of our clocks, is to assume this kind of continuous background time. If this makes sense, but otherwise our model is completely kind of discrete in the sense that all energy states are kind of discrete energy states, and kind of the ticks, kind of the signal you get from this clock comes in discrete packages. Um, but yes, there's definitely kind of a tension uh, with that how people look at time measurement. I
Paul,
hope that makes
for you,
sense. Yes.
in your statement that you just said, what is background time? Can you define that for us, please?
So this is basically like it's kind of local back. I would say like even Schrödinger time or local background time is basically kind of this the parameter under which kind of quantum systems evolve. So like given kind of the behavior of a system, which is modeled by a mathematical object called the Hamiltonian, if you let kind of this evolution of a quantum system run for a certain time, then you get to a different state, and kind of this time you let it run, that's what I would call kind of background time, or but it's something that's local, at least in quantum mechanics. And then a lot of problems, or like not so much with special relativity, but as soon as you combine it with general relativity, then problems arise.
So, in terms of quantum states that you just mentioned, is it kind of a simultaneous state, which you're considering a quantum state?
No, quantum state is, in this sense, I just took kind of a mathematical object. It kind of lives in a complex Hilbert, like a complex vector space, instead of kind of a real one as classical variables do. And there's
Got
kind
it.
of subtle differences in the description. And you have, like, you can do more stuff, and it seems that kind of on a very kind of small scale, actually nature acts this way. Like it shows phenomena as such as entanglement, and yes.
Thank you for saying the word entanglement. Alexander, your turn, sir. Thank you.
No, thank you. I just want to say I thank you for joining us today, Paul. I really appreciate that. You didn't have to do that, so I just want to say that. And Zach, you're on stage. If you have any questions, please feel free. It's an open conversation.
Okay, I'll keep that in mind. Thank you. I'll just think on you for a moment.
So, Paul, it just the last word that you said is entanglement, right?
Mm-hmm.
So, in terms of quantum entanglement, can you explain to us, just for the room's purpose? And I know what quantum entanglement means, but can you just, in your own terms, define quantum entanglement and how it relates to time, essentially?
I don't know how it relates to time, but I don't like, you can, like, there's different kind of way, like there's ways. I would just say what it is for me first. Like it's basically like kind of the possibility of systems to share an overall global state. So it can have, for example, two parts or two systems, and instead of like even like each one being in a well-defined state, they can have an overall kind of well-defined state, while kind of having individually very kind of undefined, like not undefined, but very kind of like being in the most entropic state, which is basically that all out. If you kind of interrogate the system, then it will give you each outcome kind of basically randomly with a 50-50 chance. So yes, this for me is quantum entanglement, or like kind of the basis. And how it relates to time is it's something that we still don't know. In a sense, there's kind of this there's like a paper from the 80s, which was written by Page and Wouters. So that's two physicists from the US, and they basically showed that kind of you could kind of use this phenomena of having an overall well-defined, or like kind of definite state, to kind of show that you could kind of, if you sit on one side of this, of like two entangled systems, of like one of an entangled system, and you look onto the other, you see an evolution, although you have like a static overall state. So it's kind of something like a and this was kind of like, it was kind of forgotten for a long time, and it kind of resurfaced or gained popularity the last years, and people did a lot of kind of research in this direction, and kind of now use it as a formalism, which they call Page-Wouters formalism. And yes, but it did not lead. It did lead to a lot of nice technical insights, and people generalized these things. But I think so far there's no kind of actual kind of experimental or things we can draw from this so far. Yes.
Paul, what's the name of the theory called again?
The two guys are Page,
Uh-huh.
and the other guy is Wouter. So that's Woo. TTERS.
Got it. Page
Yes, one.
Wooters.
Genau. Yes, and you will see like there's like it was written in '83, and there's like very funny, like also a little bit annoying because they basically present this very nice result that works for two parts, for two particles, and then they just add a paragraph where they say it's easily generalizable to like arbitrarily many particles, but it's actually a hard problem. And they also never wrote after this on the same topic, but people actually like 30 years afterwards managed to kind of derive nice results in this direction.
Got it.
They
Thank you
just,
so much.
yes.
Paul, so you mentioned that can you repeat the part where you said that when you stand and look back, there was a deformation? Can you rephrase? Can you repeat that?
Okay, so basically the basic result of Page and Wooters, what they show is that you could kind of like have like an overall static state, which basically is kind of a time invariant global state of systems. But if you kind of look on a kind of local and marginal perspective, if you stand on one kind of part of this overall static state and you look onto the other one, then you actually see something like change or evolution.
Okay. So Paul, wow, thanks for saying that. I
Yes.
think so after speaking to you today, I have to say I'm even more confident in my formalization of intelligence. I've been working on this for quite some time, and everything you've said today has been in line with what I've sort of come to learn. And my formalization is very simple. It's actually symbolic. And because my formalization is so abstract and symbolic, it actually gives me the ability to derive essentially all other an infinite amount of models from this one abstraction, which I think is sort of the foundation of intelligence, and that time is actually an emergent phenomena. And since it's discrete and it's emergent, what are the rules that governs the emergence of time, the interaction of time, and the evolution of time? And when you said that when you stand on one of those variables and you look back at the other two variables, you see an evolution, you see a change. You know, when I stand on, if you envision a triangle, an infinity, and a circle, and imagine that these are three-dimensional objects, and then imagine that you're standing within the circle like a Vitruvian man, like Da Vinci drew the Vitruvian man. And now imagine that behind the circle is the infinity, and beyond that is a triangle. So when you stand at that door as the Vitruvian man, what you're seeing is the evolution of time all the way to the end until it converts into a triangle. So when you were speaking, that's how I visualize it, and it's all in line with the symbolic representation that I formalized. That it's pinned up on the in the room up here. So thanks for joining us
Okay.
today, Paul. Really
Okay.
appreciate it.
Yeah, I'll try to have a look.